Okay, so in the interest of getting to lunch on time, let's begin. This is going to be the last of the complexity lower bound series, and yesterday we saw a lot of intricate reductions based on the exponential time hypothesis, and today we are going to step it up one level and look at the strong version of this hypothesis. So let's begin where we left off yesterday, which was, okay, I don't know, is this working? Sorry, should have tested this. Where we left off yesterday was ETH, which claims, okay, I think this is totally out of battery, excuse me. So ETH says that 3 sats cannot be done in 2 power little o of n plus m time, but as somebody pointed out, you could allow for a little bit of constant factor tweaking on the top, okay? So you cannot get down to like seriously sub-exponential algorithms. For example, you don't expect, I mean, ETH says that you don't expect somehow 2 to the square root of n, for example. But do you expect, let's say, for a 3 sat in particular, there is an algorithm that runs in time 2 to the 0.386 times n. Okay, that's a constant factor improvement on top. So you have this kind of running time for 3 sat, okay? But the strong exponential time hypothesis claims that you don't expect such improvements for the general CNF sat problem, okay? The mileage that you got here was because the clause length was bounded by just 3, and presumably if you're looking at 4 sat, you may again get some improvement, but as the clause lengths grow larger and larger and eventually become unbounded potentially as a function of n itself, then you don't expect anything seriously better than 2 to the n, even in the base of the exponent. So this is a much stronger comment to make about what sort of running times you expect. Surprisingly, this conjecture has neither been shown nor been refuted. Okay, it's a fairly strong statement to make, so at least one of the two things must happen, but no, we have no clue. I meant to put in a slide, which I forgot to do actually, but I should mention here that the number of people who believe the strong exponential time hypothesis is a strict subset of the people who believe in ETH, okay, which in turn is a strict subset of the people who believe in P not equal to NP, which is a strict subset of everybody working in TCS, okay. So there are people who believe P equals NP, there are people who believe P not equal to NP, but hey, ETH is not true. There are a reasonably large number of people who believe ETH is true, but SETH is not true, and then there are people who are extremely pessimistic who believe that even SETH is true, okay. But everything that you prove with the strong assumption, you shouldn't really, I mean, you can take it seriously and you can advertise it in a paper, but don't be completely shocked if someday somebody comes along and shows a 1.99 to the n algorithm for CNF sat in general. It's not considered universe shattering if something like that happens. Okay, so it may very well happen, and it may be one of your goals as well to take back home and see if you can improve the general running time of CNF sat. But as of now, like I said, there is still a constant fraction of people who believe that this is indeed true. Okay, so it's really take your pick on whether you want to believe this or not. But let's assume this as usual for the purpose of this lecture.
Why strong? Because there is no aim in it.
Not just that, the comment is about, I mean, you're actually saying that you don't even expect to improve the exponent up to even a constant factor, right? Previously, like I said, for 3 sat, you actually can improve it a little bit more, okay? And this is actually, I think this is actually after a long series of papers, this is the current best number, and there are people who work on improving this even more, so this is the usual sort of story. But here the claim is that you don't even expect a constant improvement in the base of the exponent. I mean, depending on what's more convenient for you, they're both saying the same thing. Okay, all right. So what does this mean for us? Let's say that we assume this is a given, And as usual, we are not very good problem solvers, so we're stuck with this problem for which we have, let's say, a 2 power n or a 2 power 3 width algorithm or a 2 power k algorithm, and we want to say that that's actually the best you can do, and we want to say it in a very tight sense. We don't want to say something like, so yesterday we were saying, hey, I can get 2 power 3 width, and nobody can get 2 power little o of 3 width. Okay? Now I'm saying I can get 2 power 3 width, and you can't even get to 1.99 to the power 3 width. Okay? So this is a much stronger claim, and it requires a much stronger hypothesis, and it requires a much more delicate notion of a reduction. Okay? What should, so suppose I want to show this sort of a statement starting from here. Of course, I have to reduce, but what should my n go to? Yesterday we said n going to n square or k square or whatever is going to be sticky. It's not going to give us the kind of conclusion we want. So n must be linear. Okay? But now can you even have n going to 2n, for example? If you have n going to 2n, maybe it's okay. Thank you. If you have n going to 2n, okay, so if you reduce from SAT to your problem, okay, let's say your problem has input size n or parameter k, whatever. If that n turns out to be 2 times the n that you were starting with, then if you plug in, so if you have a square root of 2 to the n algorithm, then you say that, okay, you violate SETH. Okay, is that clear? If this n was 2n, 2 times the original n, okay, and then you have, let's say, somebody gives you a square root of 2 to the n algorithm for your problem, then you can plug in your reduction, okay, square root of 2 minus epsilon, sorry. Okay. Somebody comes up with a square root of 2 minus epsilon to the n algorithm for your problem, then you say, hey, I have this reduction, yeah, I'm going to start from SAT, okay, and I'm going to get to an instance of my problem. So, and then I run your algorithm on my problem, okay, this is 2 times n, and this is roughly going to work out to a 2 minus epsilon to the n algorithm for SAT. Okay, it's easier to do the calculation with this sort of form, but it's easier to see the kind of lower bound you're getting in this kind of form. Okay, so if n goes to even 2 times n, okay, the kind of comment that you're able to make is far from what you want to show. This picture is perhaps to scale. I don't know. It's not as far as it was yesterday, but you want to again, you're kind of ambitious. You've come up with something that's 2 to the n, where or 2 to the 3 width or whatever, and you really want to say that, you know, even on the base of the exponent, I've been as smart as anybody can be. Okay, but if in your reduction n goes to 2n, then the only thing you're able to say to the world is that, okay, you can't give me a 1.4 to the n algorithm, 1.4 minus epsilon to the n, or 1.4 to the Cn algorithm, where C is a constant less than 1. Okay, this is what you're able to say, and that, well, I mean, it's nice, but it doesn't sound so impressive. It's more impressive if n goes to what? In your reduction? Yeah, if n goes to just n, right, then you're able to get right here and you're able to say that this is tight, okay? That I have 2 to the n and nobody can do seriously better, where the notion of seriously better is very serious today. Yesterday it was, okay, I mean, I have something like 2 to the n, nobody can get to 2 to the root n kind of a comment, I mean, informally, and today we are saying that nobody can even improve the base of the exponent. Again, this is a particularly interesting conclusion to draw for the setting of dynamic programming over graphs of bounded tree width, where typically the kind of algorithms we've been seeing are algorithms like 2 to the tree width, 3 to the tree width, and so forth. If you show that this is tight, then it kind of matches, it kind of formalizes your the intuition that you want to say, the intuition where you want to say that every state of the bag in your DP table is actually storing something important. Okay? Your DP table is kind of really minimalistic. Every state is there because it's doing something that the other states cannot, and you really cannot hope to seriously prune down this DP. Okay? So that's one of the reasons why we are interested in lower bounds that are based on the strong exponential time hypothesis. And for the rest of this talk, we will just see one example of a reduction for a problem that we have seen a couple of times at least during the course of this school. This is independent set parametrized by tree width. So you remember the dynamic programming algorithm? Okay, I hope that's a yes after all the tree width based things that you have done. This may be a distant memory, but it was probably the first problem for which you showed a dynamic programming algorithm. This was the party problem where you had the bosses and the colleagues and so forth. And not only did you show a dynamic programming algorithm, you also learned that you don't expect a polynomial kernel for the problem parameterized by tree width. Okay? This was by doing a slightly interesting composition and going via the improvement version. And in this talk, we will actually see that 2 to the tree width is the best that you can hope for, even in terms of the base of the exponent. Okay? All right. All of this is under SETH. Okay? So I won't be saying that too many times now. Okay? So SETH is kind of at the back of our minds. Okay? Let's just recall, since we have to start somehow now from CNF-SAT, right? Actually, the textbook reduction that we learn for independent set is often the reduction from CNF-SAT. So let's just maybe try and recall. You start with general SAT formula, okay? And you have vertices that encode a variable being set to 1 and a variable being set to 0. Okay? And then you have a vertex for every appearance of a literal in every clause. Okay? So this bunch of vertices out here, okay, is for this clause. This bunch of vertices here is for this clause. This one is for this clause. Okay? And if the independent set, so I make all of these guys complete to say that the independent set has to pick exactly one of these guys, and that sort of signifies, if the independent set goes and picks the first vertex out here, that signifies that the independent set is kind of telling me that pick X to satisfy this clause. Okay? And if it picks this one here, so why is the independent set compelled to pick one from each? Because, well, we'll set the budget that way. We will say, find me an independent set of size m plus n. Okay? Find me an independent set of size m plus n. Each of these vertices corresponding to a clause is turned into a complete graph. And between, so I have a red vertex and a green vertex for every variable. The red vertex is sort of telling me set this variable to false. The green vertex is telling me set this variable to true. And I want the independent set to just pick exactly one of these. Okay? So you can draw a matching between the red and the green vertices. Okay? So so that's sort of the semantics. Now I have to encode the nature of the instance itself, right? This I can do using even more edges. So is the semantics so far clear? I mean, I have to pick one of the red and the green vertices for each variable, and I have to pick exactly one vertex from each clause. I cannot do any better, and I need to do at least that much because I have to pick m plus n at least. Okay? So what should you suggest I do for, so now I have to say that, okay, if the independent set is saying that this clause is taken care of by X, then, well, the only way this clause can be taken care of by X is if X is set to 1. Okay? So the independent set shouldn't pick this and it shouldn't pick this and X set to 0 at the same time. If the independent set goes and picks this, it's kind of telling me that, hey, this clause is taken care of by X. Then at the same time, it shouldn't be a hypocrite and go and pick the vertex that says X is being set to 0. Okay? Because that's not going to add up. Okay? So you add adjacencies accordingly. So you say, hey, if you're going to pick this guy, don't tell me to set X to 0. If you're going to pick this guy, don't tell me to set Y to 0. If you pick this guy, don't tell me to set Z to 1. okay, because I have to set z to 0 to satisfy this. Okay. So, what happens in the forward direction is that if you have a satisfying assignment, okay, you just go and pick vertices according to the assignment. Okay. If a variable is set to 1, you pick the green vertex corresponding to that variable. If it's set to 0, you go and pick the red vertex corresponding to that variable. And from the clauses, well, every clause is satisfied. So, there is at least one literal that is okay, right, that's evaluating to 1 under the assignment. So, you go and pick that guy and notice that it will not be conflicted with the things that you picked, okay, because its only edges are anyway to the opposite of its own setting in the clause, okay. And if you have a conflict, then this guy couldn't have been the one who is satisfying this clause. Okay. That is sort of the forward direction. And in reverse, well, I mean the reverse is what we were discussing when we were coming up with the reduction. You are forced to pick exactly one each of the green red pairs and exactly one from each of the clause bags, and they must necessarily lead you to a satisfying assignment, okay, because if not, you have designed the conflicts in precisely that fashion. Okay. Is this clear to everybody? Okay. All right. So, do we already have the reduction? Bit of a pity, but yeah, we do have a reduction from CNF set to independent set, and the SETH assumption is for CNF set. But so we were blabbering something about what should happen to the n in the starting instance. What should I be concerned about in the reduced instance? Tree width. I should be concerned about the tree width of the reduced instance, right? I can actually even, I mean the fact that n goes to n plus m isn't even going to bother me as much as the fact that this is a graph that can have pretty much arbitrary tree width. Yeah, of course you can have psi. You can potentially have a very dense bipartite graph from the clauses upwards, from the clauses downwards. Okay. For a yes instance, clique size is as bad as m plus n. Is that right? Why is the clique size m plus n? You have the edges when they satisfy. Yeah, I'm taking independent set. But yeah, okay, for example, yeah, you're right in the sense that if you have a very long clause, okay, the set of vertices corresponding to that clause is a clique. So, if you have a clause on like n by 2 variables, then that guy itself is a clique of size n by 2 sitting there. No, because so I mean I've not drawn it, but each of these guys are a clique. Because in the reverse, I want to make sure that my budget of m can be satisfied only by picking one from each. If I don't make them a clique, then all my m can be satisfied from inside one clause, and some clauses can be totally left out, which will not be satisfied in the reverse. So to clique of size n by 2 is okay. That's right. That's right. But that n by 2 could potentially blow with you know with being adjacent. Okay, I mean it's okay. It's probably not a clique that's the obstruction here. Is the tree width 3n? Mm-hmm.
And for each click, you have the vertex. For each clause, you have
Okay.
the vertex with green and red.
Let's try this. We'll make at least one of Saket's papers obsolete if this happens. But just joking.
So length of the clause is what? You said?
But 2n, right?
So what did you say? I said it was 3.
3n. Okay, so we really want tree width to be n or less for proving what we want to prove. But in any case, even to get to something like you cannot do better than square root of 2 to the tree width, if you want that sort of a conclusion, then it's sufficient to prove that the tree width is 2n. Or, well, 3n would give you cube root of 2 to the 3 width, but oh, you've already lost interest. Okay. So you want to make bags from the reds and the greens, and then try to patch. So of course, the decomposition itself has to be a tree, so, and also the reds and the greens have edges between them, so there's a matching there. But that you can probably fix. Oh, you're saying red and green in one bag? Okay, sorry. Okay, then it's just a star. Fine. Right, okay.
If you look at just the clause graph, it is an independent set, right?
No, it's not.
An independent set of size k kind of thing. Every vertex is at most size n.
Every vertex is size n, meaning?
Just you can.
So, okay, I mean, I think Pranabendra is the right sort of idea, because these guys are cliques, you put them inside one bag each.
Yes, that's
right. So, so m bags with these cliques, okay, and
you put remaining 2n into everybody.
you put remaining 2n into everybody, okay, sure, and then, okay, then you just tie everything down, sure. Yeah.
The length of the clause can be arbitrary.
Right, arbitrary, but it's still at most n, okay. Why can we assume that the length of a clause is at most n rather than at most 2n? Yeah, that's right. Yeah. So if the length of a clause is more than n, there's at least one variable that occurs both in the pure form and its negation, and you can throw away such a clause, because no matter how you assign the variable, it's automatically satisfied. Okay. So all right, this is not so bad. We show that you don't expect square root of 2 to the cn, cw rather.
Cube root.
We did 3n, is it? Okay, all right. Cube root then. Fine. Anyone know what the cube root of 2 is? What?
Square root of 3.
All right. Okay. So good. You get somewhere, but I can make it 2n. Okay, that's because you don't want to compute cube root of 2, or it's too tedious. Okay, so how do we make it 2n? You probably can make it 2n, yes. Right.
Because variable side, xi may be connected to either xi or xi. You pull that.
You pull only the things that appear in the clause. Okay. Yeah, I think that's correct. You look at a clause, and instead of pulling down everybody, you just pull down the guys that appear in the clause, because those are the only edges that you need to realize, or the guys that don't appear in the clause. However, I mean, it's one of the two things. Yeah. Out of 2n, you'll pull at most n, I guess. Yeah. At most n, yes. Yeah.
Why is that wrong?
Because you're only pulling, so okay, what's going on here? So if x appears in the clause, it's adjacent to one of these guys. So basically for every, it's not adjacent to both, right? So for whoever makes an appearance, I'll just pull those guys in, and that's at most n.
No, but connectivity of these guys in whichever bag like they are. So suppose in some clauses some positive thing appears.
Right.
And, so these
But
guys
they're
are
all
different.
connected via the red and green,
Oh,
no?
okay,
Yeah, they're all connected via red and green. This guy has everything. This guy has all the 2n guys. This guy has the people in the clause plus the literals that they are seeing, which put together is again at most 2n. Okay. So fine, we don't need to know. Fine. So that's the first theorem of the talk, I suppose. But the result we are actually going to show is that you can actually modify. Well, I don't know, you modify it so much that I don't think you can really say they're modifying this reduction, but you can come up with a reduction where the resulting graph preserves the semantics of the formula and has tree width n plus a constant. In fact, it has path width n plus a constant, okay, which is an even stronger lower bound to show. I mean, I'm telling you that I even give you path width. I mean, of course, tree width is at most path width, but even if I give you path width, even then you cannot, you really need all of that 2 power tree width DP table, okay, even if you have a path decomposition. So that's a pretty cool theorem to show. So, so let's get started. We are going to, I mean, the style in which you show equivalence is, I guess, somewhat similar, but the construction of the graph itself is a lot more intricate, okay. So first of all, we are going to have some gadgets for variables. So this is always any reduction from SAT. You're going to have some variable gadgets. You're going to have some clause gadgets, and they're going to talk to each other in in a designated fashion. So what we're going to do is for every variable. So okay, ignore this guy on the top. He's no meaning. For every variable, you're going to have a path. Okay. So you're going to have n paths. Okay, of some length that we will fix later. Okay. So these are just the variable gadgets. We'll come back to these in a minute, but what we would like to have is the following semantics. So there in the previous reduction, so again when we go in the reverse, you want the independent set to kind of tell you, okay, in as clean a way as possible what your assignment should be. Okay. So in the last reduction you had a very easy way of doing it. You had 2 variables. I mean, you had 2 vertices which pretty much had exactly these semantics. This vertex was saying x equal to 1, this vertex was saying x equal to 0, and you could pick only one of them. Okay, and whatever you picked would have been your assignment. You could pick exactly one of them in any legitimate solution, and so the way the independent set was taking you to an assignment was direct. Okay, here it's going to be a little more interesting. So we're going to have these paths, and we're going to try and force the independent set. So the independent set more or less ends up picking alternate vertices on the path. Okay. Okay, I'm going to be a little fuzzy here, but basically it's going to be something like if the independent set chooses to pick all the odd vertices, then you set the variable to 1. If it's going to pick all the even vertices, you set the variable to 0. But if you're smart, you would have realized that this isn't really exhaustive. The independent set can behave in slightly different ways as well, even if it's constrained by a budget. So we'll come back and make this a little more formal. But the semantics is, I mean, so we're going to elongate a variable and spread it out across a path, and we're going to have some slightly funky semantics for how you set the variable. So this is just something to keep at the back of our minds. And then here's another gadget for the clauses. Okay, let's study this one a little bit because it's going to be important for the correctness. So here's what it's looking like. You have 2 paths, let's say one of length t, the other of length t by 2, and the t guys in between are connected by triangles. Okay. Now I claim that, okay, first of all, from this local structure, what is the largest independent set that you can hope for? Correct. So you can afford to have at most 1 from each triangle, so that's t, and potentially you can pick up the last 2. In fact, there is an independent set of size t by 2. You just pick these guys and then you pick the endpoints. That's the easiest independent set that you can think of. But I claim that something more is true. Suppose the number of triangles is even. Okay, number of triangles is even. Then I claim that any independent set that is hoping to pick t plus 2 vertices from this gadget, I mean, of course, this will go into our budget at the end, but any independent set that hopes to pick t plus 2 vertices from this gadget should pick at least one of the red vertices. Okay. What happens if you ignore all the red vertices? Notice that you have to pick both the end vertices. Okay, t plus 2, there is no way of getting t plus 2 if you do not pick both the end vertices, because the rest are triangles, t triangles. So, you have to pick the end vertices. Now, when you pick the vertex at the left end, you cannot pick its neighbor, you cannot pick this guy. So, you have to pick this guy. Okay, have to pick one guy from each triangle. So, these are both forbidden for different reasons, but so therefore, this is your only choice. Again, you can't pick this guy because he is a neighbor, you can't pick this guy because of the assumption, so you have to pick that guy. And you keep doing this, and at the end you are going to have a conflict if t is even. Okay. So, it turns out that if t is even, then the only way of getting an independent set of size t plus 2 is to pick at least one of the red vertices, no way of avoiding them. Okay. All right, fine. So, moving along, we are going to club the vertex gadgets with the clause gadgets and see how they interact with each other. So, here are the vertices, they are the gadgets are these long paths, and now I am going to actually talk about how long the paths are going to be. So, so every clause sort of gets its own little home on each path. Okay. So, you have clause 1, clause 2 up to clause m. Each clause has a zone that is reserved for it on each path. Okay. So, the first two vertices are reserved on any vertex gadget. The first two vertices are reserved for the first clause. The second pair of vertices is reserved for the second clause, and so on and so forth. Okay. And here is a clause gadget corresponding to, for example, x, y, z bar. I have appended an extra triangle. So, there are as many triangles as there are literals in the clause, but if you have an odd number of literals, I am just going to throw in a dummy triangle. Okay. Just repeat one of the vertices, yeah, so that you have you always have clause gadgets with an even number of triangles. Okay. That is going to be important for the semantics that we had before. Okay. So, what do you think the adjacencies should be? So, for x, for example, I want to say, so remember that we said something about if you pick the odd vertices. So what do I really want? I know that an independent set of a certain size, and we will of course fix the budget. Let's say that it's forced to pick at least one of these guys. That's kind of our semantics for who is going to take care of this clause. Okay. The guy that gets picked up from here, these middle vertices, okay, sorry I forgot to draw the path at the bottom, but okay. So, the guy who gets picked up from these middle vertices by the independent set is the guy who has to stand up and take responsibility for the clause. Okay. Now, on top, my semantics is going to be that, okay, if you are going to pick the odd vertices, okay, so for any variable, if you are going to pick the odd vertices, you are going to set that variable to 1. If you pick the even vertices, then you are going to set the variable to 0, okay, or the other way around. I do not remember how I did it, but we will figure out. Okay. So, for example, for x, so this guy is sort of saying that pick x to satisfy this clause. So, he should conflict with the guy that is saying set x to, he should conflict with the guy who is saying set x to 0. Okay. So, I am going to add an edge like this. Okay. If this guy is saying set x to 0 and this guy is saying pick x to satisfy this clause and x appears positively in the clause, then these two guys should not be allowed together in the independent set. Okay. So, that is the edge you have. And similarly for y. Z, however, appears negatively, okay, and I am going to pick the even guys to set z to 1, set a variable to 1. So, I am going to pick the odd guys to set a variable to 1. Okay. So, I should connect z here with the second vertex there. Is that making sense to everyone? Those are the edges. Okay. So, it was too confusing to draw the edges, but the purple guy is adjacent to the purple guy, the red guy is adjacent to the red guy, and so forth. Okay. So, the moment the independent set says I am going to pick z here, the independent set is not allowed to also tell you that set z to 1. Okay. It has to pick a guy starting at an even position, which sort of encodes set z to 0. Okay. All right. So, those are the edges that connect the clause gadgets with the variable gadgets. Okay. Yeah, this is just a repeated variable. So, just repeat the thing for x. Okay. So, it does not matter. I mean, I did not draw the edge, but yeah. So, just repeat one of these variables on the redundant thing. So, if it picks that, that still means it is picking x, and that still means that it has to say the right thing for x. Thanks. Okay. So is the semantics kind of clear? So far, we still have to fix the odd even business, but we actually have one direction of the reduction. If you have a satisfying assignment, okay, then what do? For each variable that you set to 1, you go and pick the odd numbered positions on the path. For each variable that you set to 0, pick the even numbered positions. So you're going to pick exactly m vertices from each path gadget. Okay, so m vertices for the setting. Okay, and there are n path gadgets, and from each clause gadget, you're going to pick at least that one red guy. So every clause is satisfied by this assignment. Okay, so if a clause, I mean, if this clause, for example, was being satisfied by say x, okay, then you can go and pick this guy in the independent set, and starting from this as an anchor point, you can spread and pick the length of the clause plus 2 many vertices from this clause gadget. Okay, to get an independent set of this size. Okay, is that clear? Okay, but we still have to show the reverse direction, which is that, hey, if you have a satisfying assignment of this size, I mean, if you have an independent set of this size, then you can actually pull it back to a satisfying assignment. Again, for this, okay, I mean, there are probably convoluted ways of showing that this construction already works by maybe some interesting pushing arguments, but we just want to keep things really clean. Okay, I mean, this, and one of the things about this reduction is that it's just so beautiful. Okay, so we just want to keep things clean, and we want to say that any independent set of a certain size is actually going to set all the odd numbered guys. I mean, it's either going to pick simultaneously all the odd indexed guys on a path or the even indexed guys on a path. If that happens automatically, then I'm in business, okay? Because then everything works out exactly the way we designed it, okay? But what might actually go wrong is, I think, the following. Sorry, this should have come before. So you may have an independent set that actually manages to skip even while keeping the budget. So I know that from a path of length, let's say 2 times m, okay, 2 times m is the length of each path, okay. From a path of length 2 times m, I'm supposed to pick m vertices in my independent set, and I can still do it in a fashion that's not consistent with odd even, okay. What I'd ideally like is an independent set. I would really like to say that if an independent set has to pick m vertices from a path of length 2 times m, then it has to alternate. It has to pick all the even vertices or all the odd vertices. So this is not quite true. It can do one skip. Okay, it can do one skip. So it can pick even, okay, sorry, odd, index starts at 1, let's say, so odd, and then suddenly it skips and goes to even, and then, but from there it's stuck. Okay, there's something that's basic and easy to check. Okay, connect, make it a cycle.
Probably make the path odd by adding extra vertex.
Make it a cycle.
Make it a cycle. Okay. Okay, one thing to, huh? Okay. So the news from the horse's mouth, who's come up with this reduction, is that if you try to do something like this, then well, most of what you're suggesting, the path width is going to blow. Okay, probably tree width remains small, but I don't know. Okay. Let's just take it as a given that I mean, a simple hack is likely not going to work. Okay, I mean, a simple hack.
Works, but
yeah.
Whatever all of these people are telling, it works. But this all this structure thing which you need to control, either it's very hard to do, and in some cases it just blows up because you have to do this at several places.
Add one extra vertex for each variable and increase the budget by number of variables. The independent sets have the number of variables. They are
How will
forced
you add
with
the
an
edges to the clause?
you are forced with an odd number.
Yeah, but how will you constrain that clause?
Okay, sorry. I mean, I would love this to be a conversationalist kind of a presentation, but since it's time for lunch, let's just, and like I said, I keep saying this, this is such a remarkably beautiful reduction, so let's just, I mean, because there's actually a simple fix, but it's not, it doesn't depend on tweaking the path, okay? So you don't mess around with these paths because, hey, we've worked really hard to come up with this really, really pretty thing, okay? So let's keep this as it is, okay? And so everybody clear that if there is a skip, okay, if there is an odd to even skip, it can happen at most once, right? From 2m, if you have to pick m, okay, okay, you may not pick all odd and all even, but if you get mixed up, then you can have this skip just once, okay? If you skip twice, then you cannot be picking n, okay? So hopefully that's clear. What we are going to actually do is this entire thing which we have understood very well by now, I hope. What we are going to do is we are going to make n plus 1 copies of this thing, okay? N plus 1 copies of this thing, and these copies are completely disjoint except that, okay, if you zoom in between the two copies along the paths, then I'm just going to join the paths, okay? Now we are going to do a simple pigeonhole argument to say that at least in one of these instances there are no skips in any of the paths, okay? So focus on one path, okay? So if you're going to meet your budget, of course multiply your budget by n plus 1 or whatever it takes, okay? Now to meet your budget, okay, across every path you can have at most one skip, okay? Now the first path, let's say all your paths are adversarial, they don't like you, and all of them have a skip each, okay? Because that's all that they can afford and they're going to skip, okay? The first path is going to skip somewhere. Don't think about that copy, like blacklist that copy. The second path is going to skip somewhere, blacklist that copy, and go on till the very end. You've blacklisted at most n copies, but you've created n plus 1 copy. So there is some copy where there are no skips, and everything that we argued before just works. Okay. All right. So in every path, so look at an independent set. Okay. If an independent set is bad for you on a path, that means it's skipping somewhere along the path. Now these paths are really long, right? These paths are 2m times n plus 1 length. Okay. So the first path has at most one skip. Let's say that the skip happens somewhere in this third copy. Okay. So I'm going to mentally blacklist this copy from my head. Okay. The second path skips in the first copy, so forget about it. The third path skips in the last copy, forget about it. Okay, but I created n plus 1 copies. Okay, so there will be one copy where there are no skips. Okay, it's a very basic pigeonholing argument, which just happens to work. Okay, but it's also apparently a standard gadgeting trick, so I don't know. That's what you say in the paper. So anyway, so once you see it, it's now a standard gadgeting trick in your book. So good thing to keep in your mind. Okay, fine. So is everyone convinced about the correctness that blah goes to blah and back and forth? Okay, and are we done? Yeah, we still have to show path width. Okay, so to show path width, I'm sure the smarter guys in the audience can come up with a path decomposition, like just like that. But just for fun, we are going to investigate a different way of showing that a graph has bounded path width. Okay, it's probably not that hard to construct a path decomposition. I mean, it's probably not hard to explain it, but it's probably hard to write it down. So here's a very clean argument again to show that the path width is bounded. So, but to get to that argument, we need to understand something called the mixed search number of a graph, which apparently, I mean, if this is bounded, then the path width is bounded by this number plus 1, which is a proof that we will not do, but we'll just assume this, and we'll just understand what this is and show that this is bounded in the constructed graph, and we will be done. Okay. So what's the mixed search game? So the story goes like this. You have a graph where initially all the edges are contaminated. Okay, so they're the red edges. No wonder you're laughing. Okay, can somebody pass the power cord from my bag?
No, but
It's perfect. Okay. So to begin with, all the edges in the graph are contaminated. So that we denote with red edges, okay? And what we are trying to do is the noble task of cleaning the graph, okay? And how are we allowed to do this? Huh?
Are all the edges dirty?
All the edges are contaminated. This is the word you use. Anyway, so the way you can clean the graph is by introducing people who will help you do it, okay? So you can introduce what are called searchers, okay? So at every stage of this game, you're allowed to bring in a new searcher and place him or her on a vertex, okay? You're allowed to request a searcher to slide down an edge, okay? The moment he or she does it, that edge is said to be cleaned up, okay? So you can do this again. You're allowed to introduce more searchers, by the way, but you know, the funky thing is that the cleaning is not a permanent thing, okay? Now, if this searcher just moves further down, for example, then this edge becomes contaminated again, because there is a path from a contaminated edge to this guy, okay, where no searchers are actually blocking the path, okay? And in fact, I think even this edge is contaminated. This cleaning didn't really help, okay? But what you can do to fix this is to actually place another searcher here to sort of guard the cleaned up edges, okay? All right, this is sort of a high level description. You can define it as a turn by turn process. At every stage you can put more searchers on a vertex, and at any stage essentially think of it as the well, I mean, if you remove I don't know, is it true that if you remove the vertices which have searchers, then the connected components that are left behind are cleaned? No, okay. All right, fine. I mean, so basically there is some connection to this business of separators. It's almost like the searchers form some sort of a boundary, okay, and everything that's unreachable from outside what they're guarding, I mean, and that has already been cleaned, continues to be clean, okay? But if you remove a searcher in a way that here's the zone that's still contaminated, if you remove a searcher in such a way that there is now a path from the contaminated zone to the cleaned up zone, then the cleaned up zone gets contaminated again, okay? So, okay, so this is roughly the description. You say that you win the mixed search game if you can actually place enough searchers in a way that cleans the entire graph in a finite number of turns. The constraint really is how many searchers do you need, because obviously if I give you as many searchers as there are vertices in the graph, then you really don't have anything to do. So, but can you do it with a smallish number of searches, okay? For those of you who have seen Kopp and Roberts sort of formulations of tree width and path width, this is kind of similar, although it's designed in a specific, in a slightly more specific way, okay? Fine. What we are going to do is we are going to clean this graph using at most n plus 3 searchers, which will show that the path width is at most n plus 3, okay, which is more or less what we want. And again, this is going to be largely intuitive. So the reason you can do it with n plus 3 is that to begin with, you place a searcher at every vertex of every variable path. Okay, so you place the searchers right on the left, okay. You place the searchers on the extreme left, okay, and then you generate 3 more helper searchers who are going to walk down the clause and sort of clean up the clause. I mean, it's not very hard to see that 3 people are enough to clean up this clause, and 3 is what you need, okay. So basically what happens is that you have guys moving along the spine of this gadget, okay, and somebody goes down, cleans up that vertex and comes back up, and then you move along, okay. Of course, there's a path below as well, but you know, you can move along here and then come back. It doesn't hurt. It's the same thing, okay. It's something that I just forgot to draw, but you can make it go through even if you have the path on the bottom. And maybe fun exercise, I don't think you can do it with 2 searchers. Down here you need 3. So you send 3 people from the top to come down, clean up this gadget, okay, and then these guys go back up and these people move up in front, okay. That's kind of the sequence. And you just, I mean, you have to check this detail a little bit carefully to make sure that you're not allowing for any slips, okay. So these guys that are up up front are all contaminated. Okay. So, you need to do it in the sequence that I described to ensure that you never let the contamination come back into the cleaned edges. Okay. Once you clean a clause, I mean the clause is sort of this disjoint thing that is hanging around, you cleaned it, you went back up and you carefully shifted these guys out, there is going to be no problem. Okay.
Right. You can't clean the whole clause because these guys are, so you need to parallelly keep cleaning those variables also.
Yeah, so you are doing
because
this in
those
parallel.
guys are adjacent to these triangle vertices.
Okay, sure.
So there'll be one particular thing which is
Exactly. So you
only
Yeah,
variables below.
that's
so
right. That's right.
first you clean up one variable in
Correct,
the clause
correct,
and
correct.
then move them forward.
Correct, correct. And then you keep doing this. At the very end, once you're done with one copy of the path, everything in that copy is cleaned up. Then you just take the bridge and go from one copy to the next copy. And all of this can be done. It can be done with n plus 3 searches. In any case, the reduction is in complete detail in the notes. So if you're not fully convinced right now, we can either talk about it offline or you can go through the notes. So it's really not actually this is not there in the notes. I'm sorry, it's an exercise in the notes, but it's there in the paper. Okay, so you can either look at the paper if you like, or you can stare at it and convince yourself that there is a sequence of searching that works perfectly for this sort of a graph, or you can try to come up with a path decomposition if if that's your cup of tea. Okay, or it may be even easier to come up with a tree decomposition. So I sort of welcome you to think about all of these things, and it turns out
The number of previous hit is equal to
it's +1, I think, something like this. Path width is at most number of the mixed search number +1, I think. Okay, so that sort of more or less bounds the path width of the graph by n plus 3, and we are in fact done. And as it turns out, you can come up with similar reductions for a host of other problems for which there are matching tight upper bounds in the tree width setting. I don't know. You have some examples off the top of your head for other problems for which it's tight.
Q power tree width for Q coloring.
Okay.
3 power.
3 power tree width for, okay. So dominating set, OCT, Q coloring are all examples of famous problems for which the DP that's more or less naive and not very hard to come up with. I mean, the DP is like the exhaustive DP, look at all possible partitions, look at all possible partitions into 3 parts, 2 parts. That sort of naive DP is actually tight under the SETH. Okay, so I think there's this one paper which shows I don't know, dynamic programming algorithms on graphs of bounded tree width are probably optimal, provably optimal. I always get confused. Probably optimal. Okay, so or provably optimal if you like. So you can look this up, and you have a lot of reductions of this flavor, and they're all very pretty. So have fun, and yeah, we break for lunch.
Except the one for
All right.